Thank you, Sophia, and thank you to Ali and Lori for inviting me to be here. I know that I may not be like a typical ECOOP fit, and I know that you have already listened to a talk about compositionality for concurrent or distributed program verification yesterday, and you're wondering why you are kind of seeing doubles today. But I assure you that this is going to be very, very different from what you heard yesterday. Hopefully it will match, Ilya's wonderful talk that I missed, but I'm kind of aware of the content. So just to set expectations before I start, we are in the realm of, automated, or what I better like to call algorithmic program verification. So everything that I'm going to say today, all the claims, everything that sounds outrageous to you, if you bring it down to that context, it's going to start to make sense, hopefully. So with that, I stole one of Ilya's slides from yesterday. And this is, the claim that Lamport made back in 1997 about compositionality not being really something desirable for program verification. And I want to kind of use this as the grounds to kind of pivot in a different direction than Ilya's talk went, and tell you about a particular type of compositionality that we have been exploring for almost 7 years now. And this is something that is useful both specifically for algorithmic verification and also for categories of problems, certain type of programs, certain type of properties that compositionality could, in the classic sense that you know about, could actually make things difficult, and this alternative view could be helpful and complementary in some sense. Okay, so here is a really kind of sad early history of concurrent program verification. Sad because it's so sparse and shallow, not because the early history is actually sad. So I just wanted to kind of outline some very, very early developments in concurrent program verification, mainly, and leave the rest out because algorithmic verification is sort of still stuck exactly in this picture. All the wonderful kind of developments that have happened in program logics after 1981 until really present day, they're very nice for people to manually develop proofs, but for algorithms to actually use them, they're not really useful, because they all rely on this kind of human ingenuity to feed insights, concepts into proofs, which a computer cannot come up with that easily. So we just wanted to quickly kind of contrast what Floyd did compared to what Hoare did, which is just giving an inductive annotation to a program as opposed to trying to kind of do it compositionally through building blocks, Hoare's logic. And then exactly Ashcroft was the first person who said that, okay, if you know how to do sequential programs, we can do concurrent programs by just basically encoding the concurrent program as a sequential program and then going ahead as we knew how. And then Oiki-Grease method and Jones's relay guarantee came to say that, okay, this is not good. We want compositional, so we want to do compositional things. But algorithmic verification has basically failed to really deliver on this front because of the known kind of incompleteness without auxiliary variables problem. Auxiliary state is really kind of an insight that has to come from humans to do these proofs well, and algorithms can fake them, but usually, if they're simple, such as you don't need auxiliary state at all, they succeed wonderfully. But if it's complicated, they basically fail. They fall back and collapse into Ashcroft's method, which is basically about encoding the entire state. And, all these methods, other than Ashcroft in some sense, are advocating this decomposition of the proof over program structure. And I want to say that maybe if algorithms cannot really see and have insight well, maybe we can do it a little differently, right? And this particular different method is inspired by something that, for me as an undergrad, it was the first, exposure to actually proofs of things before I actually learned formal verification. And that is, when in algorithms books, we were given algorithms and we were supposed to kind of do what they consider formal, we consider an informal reasoning about why algorithms are correct. So what am I talking about here is just, a snapshot of one of my favorite basic algorithms. computing the convex hull of a set of points, right? So the reasoning in that book, famous book for computational geometry, for why this algorithm that they're giving for convex hull is correct, I'm not going to go over this because this is a little besides the point, is basically a combination of sort of induction and the fact that we kind of look at the case analysis for the algorithm. We say that, if the next point that we are considering is here, has these properties, the algorithm reacts this way, therefore it does the correct thing. If it's the other way, the algorithm does this other thing, and it still does the right thing. So by this kind of case analysis, and there are a few cases that have to be considered, plus this inductive kind of underlying induction, they basically argue why the algorithm is correct on all inputs, right? And I want to basically try to argue with you that this sort of thinking about program proofs could be helpful for concurrent program reasoning as well, for certain types, and especially for algorithmic verification. And I will basically give you two instances of the instantiation of this kind of thinking for these proofs, and hopefully I will convince you by the end of this talk that I'm not completely off. Okay? So, the general idea of that algorithm starting to become formalized in what we consider a formal proof is based on this really simple observation that if we wanted to kind of avoid proving the entire program correct the way we know how already, we can try to instead prove it kind of what I call trace by trace. I know trace is a really loaded word and it means very different things to very different people in this room. Think about a trace of a program as basically just a sequence of the statements of the program with no semantics attached to them. So this is really just a word, right? So here is a simple trivial proof rule that everyone should accept immediately from me, that if I prove every trace of the concurrent program or the program in general correct, then I have proven the program correct. And the idea is really kind of that simple, the underlying idea, that I want to take one trace at a time, prove the trace is correct, but naturally not just that one literal trace, but all the things that belong to the same case in the sense of the algorithmic cases that I just mentioned to you in that example, correct with that one trace. And then if I do these kind of case-by-case things with the optimism of a few cases are going to suffice, I will end up doing a few, finitely many, of these sort of proofs, and some sort of combination of these proofs is going to give me the proof for the program. So that's how I'm mimicking that simple case-by-case proof of the algorithm that I mentioned before. Okay, so more specifically, how do we make this work for programs, and what are the problems, the algorithmic problems that have to be solved for this to actually become an algorithm that can work. So take all syntactic program traces. We can immediately partition them into two sets, the sets of feasible traces and the sets of infeasible traces. So a feasible trace is something that corresponds to at least one concrete execution, and an infeasible trace is something that there is no concrete execution associated with it. Okay? And I want to kind of change correctness just a little bit from the simple rule that I showed you to something that is more convenient to talk about. Equivalent notion, but more convenient from this point on. And the convenient notion is I want to take the error traces of the program. So think about these as traces that violate the post condition, or traces that go to an error location of the program, something that basically is violating a property that we care about. And if I show that all the error traces of the program are infeasible, I have effectively proved the program correct. So this is, in a sense, my new proof rule that I care about. Now, my job is to show that all the error traces of the program are infeasible. How do I set this up in an algorithmic verification setting? I basically create a refinement loop in some sense that we all know about, a version of it. So I want to take an infeasible trace, I will prove it correct, and I will generalize the proof of correctness to the proofs of correctness of all the similar traces in some sense. So now I have proved multiple traces correct, but in most cases not the entire set of error traces. I have some coverage. I want to be able to ask the question, am I done? The answer would be no, and I will get another trace. I will generalize the proof of correctness. I will get a little more coverage. In some cases, when I combine the proofs of correctness for these two traces, I will get even more coverage than the individual generalizations. And I will continue doing this until I cover all error traces and I have a proof. So this way, one algorithmic unit that should be already obvious to you is, how do I do this? How do I generalize the proof of correctness out of one trace into many traces? And then the second thing is this check, right? I should be able to perform a check. Am I covering the entire set of error traces or not? And if not, I should be able to return an actual counterexample, something that says that, okay, actually the program is not correct. Here is a concrete one. Or, you don't have a concrete counterexample, but you haven't covered everything. Here is another trace. Prove it correct, and you will make progress. So if I have these two units available to me, I can kind of put them together, put them in this refinement loop, and then I have an algorithm. And then I can basically continue proving things. Now, before I get to specific things, I want to point out that if you look at the way that this thing that is right now completely schematic, I haven't really kind of instantiated for you, as a proof method, in some sense it is compositional because I am proving simple things. These are proofs of individual traces that are like simple, branch-free, loop-free, sequential programs. And I'm taking these simple proofs and kind of putting them together as the proof of a more complicated entity, which is the entire program. So I'm still kind of doing some sort of compositional work. But unlike methods that you know about, the kind of separation lines for compositional reasoning are not lying at program structure like boundaries of threads or procedures or things like that. So there is this contrast that is happening here. Now, there are advantages to doing this sort of decomposition. One advantage is, when I do proof construction for these simple entities that are individual traces, I can do logical reasoning in a domain which is simple, right? These simple programs that I mentioned. And I don't have to care about all these complex program features mixed with my logical reasoning. Now, the advantage of this is, one, I don't have to care about complex program features. Two is this kind of lets me completely decouple myself from the program features in a way that I cannot convince you right now what is useful, but I want you to kind of remember this so that I will deliver this to you really concretely at the end of this talk. That it's not just difficult sometimes, it's almost impossible to try to tie yourself to complex program features. The second thing is the part that is about checking a candidate proof has no logical reasoning in it anymore. I want to do this purely combinatorially. Meanings of program statements, meanings of proof statements, all of these things are not relevant at this context anymore. So this will be a pure combinatorial check, and as a result, I can use all the combinatorial reasoning. This is coming from the finite state reasoning of model checking. There is a large 20-something-year-old history that tells you if you are in a finite state domain, you can use this array of techniques to do better. And all of that all of a sudden becomes relevant to this part, and it wasn't before when I was looking at a combined program. So beyond kind of just trying to do it a different way, I will get these advantages as well, which are really important for algorithmic verification. Maybe not for humans, but for an algorithmic verification, they're really the key. And right off the bat, I want to kind of throw in this disclaimer that I'm not performing magic by just doing this separation, right? If something is fundamentally hard, that hardness still exists in this method. The only difference is I try to do the hardness in the combinatorial part more, which is kind of something that I can be more effective because I don't have to mix logical reasoning. And I want to push it outside the logical reasoning, which is very limited when you want to try on automated theorem provers or SMT solvers that have limited scope of applicability. So just take it from one place and push it to the other place, not making it disappear like magic, right? That's the only thing that is happening. Okay. So I've listed a kind of series of instantiations of this framework that I've told you about. There are other instantiations that were not my work, and the slide was already kind of filled in, so I didn't want to kind of make a really long list. This has been applied to sequential programs, to programs with procedures. We started looking at concurrent programs, and we applied it to concurrent programs by taking the proof generalization to be through the concept of inductive data flow graphs and the proof checking through alternating finite automata. Then we did proofs of unbounded concurrent programs by basically inferring automatically counter auxiliary variables. Today, I want to talk about the last kind of 3 items in some sense. I want to give you an example of how we instantiate this framework for the verification of unbounded concurrent programs that are basically parameterized concurrent programs. With safety properties, I will just mention liveness in passing so that you see a classic instantiation of this framework. And then I move on to kind of more recent work that I'm super excited about, which is not even like a classic program proof. It's about proof simplification for concurrent programs. And there I'm hoping that I can really deliver to you why this kind of detachment from program structure has a lot of advantages beyond just, you know, the ones that I gave you on the earlier slide. So I'm hoping I will have time to give you 2 full instances through this talk. Okay, let's start with the first case, parameterized concurrent programs and safety proofs. And I will start with an example right away that I'm hoping almost everyone in this room already knows about. These are ticket locks that I have written using a simple kind of schematic code. We have 2 global variables, S and T, the ticket value and the service value. And we have a local variable M that is basically the local ticket number for each agent. And this is supposed to enforce mutual exclusion. So the way that we deal with these things is we kind of want to say that we have arbitrary number of the instantiations of this code, and we want to prove that the mutual exclusion property holds. So for safety and non-starvation for liveness, which I will very, very, very lightly just touch on. So what are the challenges? I have unboundedly many threads, I have shared memory, and I have infinite data domains. These kind of 3 complications for algorithmic verification. Shared memory, infinite data domains, clear. The unboundedly many threads, for those of you who are specifically not tuned to automatic program verification, I wanted to just kind of make this simple observation that the moment that you have a local variable, even if your data domains are finite, just the fact that you have unboundedly many copies of that local variable, it means you can basically encode unbounded data even if your local variable is a Boolean, right? So that sort of complication is there even if you kind of drop one of the assumptions and make your programs less rich. And more importantly, if I wanted an actual program structure to kind of hold on to and decompose the proof over, the program structure that I'm dealing with is an infinite control flow graph. So that is what makes things complicated for automated verification. So I have, you know, or I have to do it in a parameterized way. Do it, you know, for all n, a control flow graph with n threads is going to be correct, right? So the way that we deal with this is we say that, okay, let's take the control flow graph of 1 copy, and this is going to give us a simple automaton. This automaton has its states for control locations of the graph, and its the labels of its arcs as the program statements. What we do is we take this as an indexed alphabet that the statement of each thread is going to be labeled by basically the thread ID. So now if I have 1 control flow graph and I have the labeled statements for that, I can basically produce the control flow automaton for the product of these things by basically just interleaving the runs. Okay? But still I don't want to look at infinitely many of them at a time. So let's look at safety. So proof construction. The 2 kind of elements that I told you that I have to instantiate to have an actual refinement loop that would work algorithmically. I want to tell you about the first element. I will take a run, a trace that I haven't covered yet, and I want to prove it and generalize its proof of correctness to many traces. So here is an example of such an error trace. This is a trace, a syntactic trace that is violating the mutual exclusion property. Why? First thread is getting a ticket, entering. The second thread is getting a ticket. The first thread is entering the critical section, and following that, the second thread is entering the critical section. So now both threads are inside their critical section. If the code is correct, I should be able to prove this is an infeasible trace. This cannot happen. And, this is a really, really simple case. I can, easily give it a proof. But before I do that, I want to make a simple but really important observation right away. Here is just one trace. But I want you to note that if I take any trace that is a violation of a safety property, the violation of a safety property, by definition, is always a finite length trace. And a finite length trace always has the participation of finitely many, boundedly many threads in it. So it could be 2, as it is this case. It could be 15. It could be 25. But I know it's bounded, which means that I can just prove it correct and not care about how many threads are participating in it, right? And that is exactly, what we exploit. So I prove this trace correct. This is, you don't have to read that proof. It's really not essential to my presentation. But you believe me that I can give a proof of correctness to this trace. So I have proved it correct. What is going to happen now? I want to try to generalize this proof into proofs of many things. How do I do this? I extract Hoare triples out of the, out of the proof of this trace. So that Hoare triple that you see, let me try to do, oops. Somehow I can't get my pointer here. Okay, so this is the Hoare triple that I have extracted out of that trace basically, and I can do the same thing with different parts of the trace. So the second one is a Hoare triple that I've extracted kind of out of this, in some sense getting true and this post condition. These are all valid Hoare triples. The third one here, and so on and so forth. So I can extract as many Hoare triples as I care about out of this. And the part that I'm not showing you is, once I have these kind of atoms that participate in my Hoare triples, there are these extra trivial Hoare triples that I also throw in the mix, which are what I call the stability Hoare triples. Things that maintain, all the program statements that maintain a precondition or postcondition true. I will also throw those things in, but they're not on the slide because it would make it really messy. And then the moment I have actually a set of Hoare triples, I want to pretend that in some sense I have a general proof. So in what sense a set of Hoare triples is actually a general proof? In this particular sense, that I can use these kind of Hoare triples as basic atomic blocks, and then use combinatorial operations to combine them together and get proofs of other traces. So what do I mean by that? Sequencing, a basic Hoare logic kind of rule. I can take 2 Hoare triples that the precondition of one matches the postcondition of the other, and I can combine them together and get a proof for a trace which is now, containing the concatenation of the two. One thing that I want to note right away here is that at this stage, I want to not do any more logical reasoning. So when I say pre-post conditions match, I mean syntactically. I don't want to check an implication, anything like that. If they match syntactically, like Lego pieces, I will put them together and I will move on. Okay? So the other kind of building block combination rule is the conjunction rule of Hoare logic. If I have the same statement with different pre and post conditions, I can take the conjunctions and I can strengthen my post condition as a result. And the third one, which is really important for unbounded thread verification, is the symmetry rule, in which I can say that as long as I know I have a replicated copies of the same program, if there is a rule that refers to, let's say, thread IDs 1 and 2, then I can say that the same relationship is going to hold between thread IDs 11 and 22 as well. So I can basically, even just using this one rule, once I have one Hoare triple, I have infinitely many Hoare triples that I know to be true by just renaming the natural numbers to other natural numbers. Right? There is a rule, right? If 1 and 2 are different, 11 and 22 have to be different as well. But as long as I do the mapping properly, I have basically a rule. So if I take these three kind of combination rules, a sequencing, conjunction, and symmetry, and a set of basic Hort triples, and I close the Hort triples under these rules to get all the Hort triples that I could possibly infer as a result of these, I will basically have this object that we call a proof space. So the analogy here is a little kind of like vector spaces. You have finitely many vectors that define a vector space, and basically, an unboundedly many kind of vectors that are in that space. And here, I'm interested in finitely many Hort triples that basically prove infinitely many traces correct. And this way, once I extract these elements out of the proofs of one trace, I have effectively proofs of correctness for a lot of other traces which use the same ingredients. And that is the idea of my proof generalization. All right? So in the particular case of ticket, if I add one more Hort triple, which I can get from one more counterexample other than this one, I have now effectively the complete proof for ticket, modulo the Hort triples that I told you that I'm not showing you, the stability ones. This is basically the complete proof for the ticket protocol, right? So it's very neat that one can basically get it out of two counterexample runs. So 2 cases, and you prove your program correct entirely. Okay? Now, I will tell you, I'm yet to tell you how proof checking works, but before I tell you how proof checking works, to kind of make proof spaces concrete, I can tell you one result, that Ashcroft invariance, which basically corresponds to giving proofs with universally quantified invariance over thread IDs for parameterized programs, proof spaces are basically complete with respect to this. Whenever you have a proof of that sort, there is a corresponding proof space that basically proves the program correct. So basically anything that can be proven that way can be proven this way as well. So we know that this is not just some random invented thing. It's actually concretely tied to something that people would use otherwise for this sort of proofs. Now, proof checking. So for proof checking, I need to be able to perform this check. Is the proof good enough? And if it's not good enough, I should be able to return a counterexample to kind of continue enlarging the proof, right? So the key that I'm emphasizing yet another time is that when I go to the proof checking unit, I want to do only combinatorial reasoning. I've already done my logical reasoning by basically doing the proof of the trace, extracting the Hort triples, computing all the stability Hort triples, and basically computing this object, which is some sort of automaton that would represent the proof space. And then at this stage, I will have a representation of the program also as an automaton. And these automata, both for the proof and for the program, refer to natural numbers. They're basically infinite state automata. These are the automata that we actually invented, which we called predicate automata. These are, their states are predicates over natural numbers, basically. They correspond to alternating finite automata, if you happen to know what those things are, where the predicates are just standard propositional, finite state predicates. So why would proof checking using these things work? A collection of 3 non-trivial but simple to state results. One is that the language of the program traces for parameterized programs can be represented using predicate automaton. The other one is that the set of traces that a proof space proves correct can be represented using predicate automata. And then therefore, predicate automata have the usual Boolean properties that are desirable for automata, which means that we can basically state the proof coverage, the proof checking problem, as a language inclusion check. Is the proof the language of proof subsuming the language of the program? Is the language of the program a subset of the language of the proof? If yes, we're done. If no, we basically get a witness for this inclusion not holding, and that witness is basically the counterexample that we use to kind of progress. Now, there is a good news and there is a bad news. The bad news is that testing the emptiness of predicate automata in general is undecidable, which is expected because I cannot perform magic. And algorithmic verification of parameterized concurrent programs is in general undecidable. So I cannot break that decidability barrier. The good news is that in a very sensible case, which we would expect, the sense of monadic proofs, we have decidability. But this is not the only one. There are other kind of interesting cases like bounded 3-bit, bounded programs that there are more decidability results. So in cases that we really expect the proof to go through, it does go through, but naturally, in general, we are basically slaves to the same undecidability results that any algorithm would be. And this result is, this decidability for the monadic case is a very neat result that kind of differs to well-structured transition systems. And this is kind of the point that I was trying to make at the beginning, that once you are in the realm of combinatorial reasoning, there is a wealth of research. For example, the research into well-structured transition systems that you can kind of borrow and use for your elements, which we couldn't do if we were dealing with unbounded data, if we hadn't separated logical reasoning from this. Okay, so I want to make a few kind of high-level points about the advantages of this particular thing for parameterized concurrent programs, then mention liveness, and then move on to the second part of the talk. So, the first point is kind of repetitive. I can use loop invariant discovery, this kind of efficient model checking techniques in 2 separate units, all the knowledge, and combine them together to have more complicated things. Effectively, I'm using basic logical reasoning to get implicitly, not explicitly, quantified invariants for programs. And this is something that I find really exciting. The second thing is this liberation of proofs from program structure comes with this sort of advantage, and the advantage is when you're tied to the program structure, then you need to invent auxiliary variables to make your proof go through. Once you do this, we can actually prove that the proof system is complete without the need for auxiliary variables. So proof spaces for instances like Boolean programs, parameterized Boolean programs, are complete without the need for auxiliary variables, whereas if you wanted to do classic compositional reasoning, you would still need auxiliary variables to basically be able to claim completeness. And finally, if you are kind of even a little bit familiar with algorithmic verification, you would know that if you don't want to buy my technique, the standard thing that people would use would be predicate abstraction. First, abstract your program into a finite state thing, then reason about it. And that sort of reasoning, when you choose your predicates a priori, is not going to be refutation complete, because if you make a choice of the wrong predicates, then you cannot prove the program, but you don't know why you cannot prove the program. Whereas in my technique, because we never commit to predicates in advance, whenever the proof is not complete, we know why we are not complete. We get a counterexample, we can kind of continue. And basically, that's the final advantage. So with that kind of short overview, I mentioned safety to you, that proof spaces are used as a kind of concept to generalize proofs of correctness, and predicate automata are handling the backend, the combinatorial reasoning about proof checking. And we can kind of extend this to liveness as well, which I'm not going to kind of tell you about that much. I decided to kind of opt for something else. So with liveness, we can still use proof spaces, except we have to enrich them with these extra components, basically ranking functions, to be able to reason about termination as well. So well-founded proof spaces are proof spaces that now additionally have this kind of ranking functions in them. That part is really more or less a trivial extension, so we don't pay a lot of price to do the extension there. But as a result of doing a simple kind of generalization, then there was a hell of a price to pay to actually make proof checking to go through. We had to basically invent quantified predicate automata to be able to first represent the programs, because now we needed to kind of capture lassos in the programs and then check that the lassos are basically included in the lassos of the proof. So there was a lot of non-trivial work that went into kind of making proof checking work for liveness. But I thought that this crowd might not be really that interested in the details of that. So I'm skipping that, and I want to tell you about the second part of my talk, which is this kind of non-trivial program verification problem. Non-trivial is a bad word. Non-classical kind of program verification problem. So what is this? In this case, I want to talk about bounded concurrent programs, and I will tell you why in a second. And I don't want to just prove the program correct. I want to prove the program correct in a sense of finding a simple proof for the program. And the simple here is not a human simple, it's a machine simple. So let me start by giving you one example and make this clear what I mean by this. So here is a simple piece of code with two methods, increment and decrement, that you have seen, I'm sure, everywhere. So an atomic increment and an atomic decrement, except the decrement is a blocking decrement. The idea is that if it cannot decrement and maintain non-negativity, it would just block and it wouldn't decrement. So the key observation for this part of my talk here is related to commutativity. The blocking decrement, if you think about it for a second, semi-commutes against the increment. What do I mean by this? If I have a run, the dots are the parts that I don't care about, a program trace, that the decrement and the increment happen to be next to each other in this order. I know I can swap the orders. And the only thing that will happen is the set of reachable states at the end of this trace can only remain the same or increase, which means that if I prove this trace that you see now infeasible, I can deduce that the original was also infeasible. But the converse is not true. If I had this and I were to swap the decrement to before the increment, the decrement might actually be non-blocking here, but if I swap it to before the decrement, it might block. So I may actually shrink the set of reachable states as a result of this. So I have only this semi-commutativity property, right? The decrement moves to the right of the increment, but not vice versa. Okay? Now let's look at this simple concurrent program that is using these two. I have two loops. Each counts up to m or n, and calls decrement or increment in the loop. And I want to say that when I'm done, the accumulator is going to have the difference of the two. Keep in mind that certain runs of this concurrent program might just block and never reach the end. So I'm in the safety realm now. I want to only show that the runs that actually reach the end satisfy that post condition. I don't care about the ones that block. Okay? So if I apply the semi-commutativity property that I showed you in the previous slide, it means that I can take any run of this program and push all the decrements to the end, because all the decrements swap over all the increments. But more importantly, every other statement that you see in this program is thread local in a sense, and thread local statements always commute with no problem, right? Which means that I can take this program and turn it into this sequential program, and I can claim that I can soundly verify the sequential program in place of the concurrent program, right? I've only basically used the commutativity of other statements to neatly bring all the relevant statements together. So this is all good. This is trivial stuff. You will believe me when I say this. But not really quite yet interesting. But I want to use this to kind of introduce this concept to you, that this sequential program I want to call a reduction of the original concurrent program. What do I mean by a reduction? A reduction of a program is another program that basically can be soundly proved safe in place of the original program, which means that it soundly represents all the behaviors of the original program. Now, let's make the example interesting now. I've changed the increment and the decrement only by changing the delta. It's not +1 or -1 anymore, it's +d or -d. The semi-commutativity properties haven't changed. Still, decrement semi-commutes with increment even if the delta is d, in the same exact way, for the same exact reason, right? So I still have that. So if I go back to the same program as before, that now uses some global constant c instead of 1 to do this decrement and increment, I'm going to slightly change the pre and post condition, and you will see why in a second, to just say that if n and m are at the beginning equivalent to each other, and I increment by c n times and decrement by c m times, at the end the counter has to be 0. Okay? Because the same semi-commutativity properties hold, I know that I can get the same sequential reduction that I showed you before. But now the twist is this. For automated verification, this sequential reduction is useless. Why is this useless? because the invariant that I need to prove this sequential reduction correct is a nonlinear invariant now. I need to actually establish by the end of the first thread that I have n multiplied by c in counter y, so that then I can, at the end, start decrementing that down and arrive at 0. And nonlinear invariants are not really good for automated verification. And maybe there is a tool that I can actually handle this a little bit. This is just an example, right? I want to basically tell you that once the invariants for sequential reasoning become complicated enough, getting a sequential reduction is really not desirable for simplifying verification for a machine. So now, what can I do if I wanted to prove this program correct? Is there basically an alternative? Is there a different reduction of this program that would have a simple proof? Yes, there is one. I can go back to the original concurrent program, and I can look at the lockstep reduction when basically the two threads execute in lockstep, and I want to only look at those behaviors of this program. So when the two threads kind of move at lockstep, I can always, at the header of these two loops, when the one body executes and the other body executes and catches up with it, have a simple invariant, which is basically y is always 0. You increment by c, you decrement by c, you're back to 0. You increment by c, you decrement by c, you're back to 0. Which means that with a simple y is equal to 0 invariant, I can prove this particular reduction satisfies that postcondition easily, no need for nonlinear reasoning, right? So this is the desirable reduction for the automated method compared to the sequential reduction that you saw before. So if I haven't made my point to you yet, and you say that, oh, okay, so we do sequential, we do lockstep, is there anything else? I can modify this program easily and get yet another reduction. But before doing that, let me quickly reason for you and tell you why this particular reduction, the lockstep reduction, is sound. So that we are all firmly on the ground, we believe what is happening, so we can continue. So I already told you about the semi-commutativity property of decrement against increment. So I know that that is going to hold still, right? Whenever I have a decrement before an increment, I can push it to after. But there is something far more interesting that is happening, and that is the fact that in certain contexts in the program, but not in all contexts, I know that the decrement and the increment fully commute. If I'm anywhere in the program and in my history I have more increments than decrements, which means the counter has enough value in it, then I know that an increment also commutes to the right of an increment, a decrement. So in all contexts, I have the semi-commutativity property. In certain contexts, I have the full commutativity property. And I can use this to actually kind of convince you why that reduction, the lockstep reduction that I showed you, is sound. So I would have two types of runs. I have the types of runs that, like this one, every other statement I have dotted because it's not really important. That's, for example, if I start with a decrement, right away, I will get an infeasible run, right? It will not correspond to an actual execution because the decrement is going to block and I cannot do anything else. So these kind of runs, I don't have to reason about, by basically commuting things. I can easily prove that these are infeasible and move on. The runs that are more interesting are the ones that are actually feasible, but the increments and decrements are not in lockstep the way that I care about them. And here I can say that, okay, look here, at this context, I have more increments than decrements. So I can basically, commute those two things. Then I can move down to this context. I have more increments than decrements in this again, at this point. I can swap these two things, and now my run is neatly lockstep. Increment, decrement, and so on and so forth. So I can basically, argue that every run is going to be equivalent to a lockstep run if I use both this contextual commutativity and the semi-commutativity arguments that I mentioned. And those are basically the key concepts here in what I'm trying to present. So now, here is a modification so that you are convinced once and for all that these reductions that I'm talking about could be arbitrary. So if I just modify the program ever so slightly, make the bound for that loop to be 2 times n, and make the increment in the delta for the decrement to be 2 times c. The pre-post conditions have to still hold, but the reduction that now I need to do the same kind of simple reasoning is not lockstep anymore, is 2 steps of the left thread as opposed to 1 steps of the right thread. And that is going to give me the nice reduction with the same simple invariant as before, right? And I can play with this program, and I can produce any sort of reduction that you can imagine. And this is basically the fundamental point in the problem that I want to pose, which is, can we do this? Can we feed a program to an automated verifier that has a complicated proof for the entire program, but has a simple proof for a sound reduction of the program, and ask for that simple proof to be produced so that the automated verifier can actually do it? Is this possible? And my answer is yes. We can do this by taking the same framework that I told you about and reinstantiating it to solve this problem. So if you remember, I gave you a proof rule at the beginning, which was, I want to prove all error traces infeasible. So I still want to do that, except, instead of all error traces, I want to prove a reduction of the error traces correct. And I'm going to use this kind of a schematic of like a slice of the ellipse as, graphically representing a reduction of the set. So now, if we pick this particular reduction in advance and go ahead with automated verification, it can just be the wrong reduction, right? It can be that this other reduction that we didn't pick is the right one, like the examples that I showed you already. Which means that instead of, picking one in advance and then starting the refinement loop, I want to be able to talk about all reductions. So I have basically lifted these things, sets of infeasible and feasible traces and the sets of error traces, to sets of sets. So I have a sets of infeasible traces, and then I have a sets of things that are not only infeasible traces, feasible or infeasible traces that I've called mixed traces. And I want a new proof rule that says that a program is correct if all its reductions are actually, included in the sets of infeasible traces. So I mentioned all reductions, and it would be the case if the program is correct, any of its reductions is correct, which means that all of them should be there. But what I don't actually care about is all. What I care about is I can prove one of them only correct. That would suffice. Which gets me to this new picture in some sense. So I have divided the sets of infeasible traces into 2 subsets. I have the easy to prove ones and then the hard to prove ones. And this is from the point of view of an automated prover. And my error traces, the set of all reductions of error traces, would be still in the combination. But I'm basically looking for this kind of golden egg, one reduction that its entirety is in the blue part, in the sets that are easy to prove, like the one with the simple invariant as opposed to the one with the nonlinear invariant. And I want to kind of set up a refinement loop to find that thing for me, right? So I need to tell you the 2 elements, the algorithmic elements that I mentioned before. I need to tell you how I would do proof generalization, and I need to tell you how I do proof checking. And once I put these 2 elements together, I have constructed the refinement loop for you for this particular problem. So proof generalization is easy. I don't want to do any innovation here. I will still take a trace of the program, and I still prove it correct as before. Except that because I'm in the realm of bounded concurrent programs now, I will drop the symmetry rule from proof spaces that you saw before. I will only do sequencing and conjunction, because I don't care to extend to unboundedly many threads. Otherwise, I will generalize exactly as I told you for proof spaces. Because I'm dropping the symmetry rule, though, I'm now in the realm of finite automata. So whenever I have a bunch of Hoare triples, the generalization of the proof would be a finite automaton, a finite array language, a normal standard regular language that you know about. So my proofs would be regular languages as a result. So nothing new here. Proof checking is the place that I basically push all of my innovation to make this work. So I need to kind of tell you how I would represent infinitely many program reductions. And then I would check these infinitely many program reductions against a regular proof that I just mentioned I would trivially construct without putting any new effort into it, right? So I will tell you how we construct the reductions, and then I will come back and tell you about how the proof checking makes sure that things are same algorithmically. So for the reductions, we use this notion of automata, which just took us a long time to discover. It wasn't at all kind of like a trivial choice, but it works wonderfully well, and I'm actually really, really excited about this. So these are looping tree automata. So why looping tree automata, and what are looping tree automata? So if you know about Biuki automata, looping tree automata are kind of a specialization of Biuki automata with trivial acceptance conditions. They basically accept any infinite tree as long as there is, an infinite tree. So, but why trees? There is a simple, in hindsight, observation, and that is that a tree represents a language. So think about a Boolean labeled tree like the one that you see on the slide. Any path from the root to a true can represent a word in that language. And any path to a false is something that we don't care about. And now, think about an infinite tree. An infinite tree can represent an infinitary language. It's a language with infinitely many elements in it, which is basically infinitely many words in it, which is basically programs as we care about them, right? So programs, individual programs, can be represented using infinite trees. Now, looping tree automata that admit infinite trees can therefore represent basically sets of programs, sets of languages, instead of just flat languages. And this is really the key. So now, but more importantly, once I know how to represent languages as infinite trees, I can represent reductions of languages, especially up to commutativity property, as pruned trees. So the tree that I showed you about, I can kind of say that, if A, for example, semi-commutes against B and D, and A, B, and D are program statements, just schematically, I can say that if I'm kind of exploring this tree in a kind of prefix traversal, if I first see the left branch, then the grayed out branch that you see there is an equivalent word that I can drop up to commutativity. That's an equivalent word. So I can drop it from this tree. I have now reduced the tree further. And then this grayed out word and this bottom corner is equivalent to the other one on the side, so I can drop that out. So anytime that I'm any kind of traversal strategy of the tree that I have in mind, it first sees some strings and then prunes the other equivalent strings that sees later in favor of the strings that it has seen before. And exactly based on this observation, every traversal strategy is going to give me a different reduction. Which one I see first, which one I throw out as a result. So if I enumerate all such traversal strategies, they would basically give me different reductions of this program up to commutativity properties. This way, luckily, I can actually encode this in a looping tree automaton. So a looping tree automaton can therefore represent all these kind of pruned program trees up to commutativity, any way that you can traverse it, and therefore it represents all, these sets of infinitely many reductions of the program. It's basically as simple as that. So pick your traversal strategy, you have one reduction. Enumerate them all, you have all possible reductions over the program. As simple as that. I kind of already covered this one. So let me just quickly kind of underline the key point of this work, which is, statically, if I have commutativity relationship, this is, well and good, we can deal with it. But what happens to context? What happens to the contextual commutativity things that I showed you in that example, which are really essential to get nice, good reductions? So here is a schematic that I'm hoping I can make my point using without getting into too much details. If you're at any point in the program and sigma is a trace of the program, which is your history, and A1 through AK are your next steps to take, you can basically augment your program with these extra statements, which are basically assertions that are saying, whether A1 and A2 commute, whether AK and AK minus 1 commute. And your program has now these extra statements in it. And whether those kind of blue blobs that I'm showing you at the end are reachable or non-reachable, it basically is the same as whether two statements that they talk about do commute or do not commute in this context. So by enriching the program like this, we let the prover at any point in time not only prove certain runs of the program correct and generalized, but we let it also, by looking at these blue statements and the blue blobs, also infer commutativity predicates that help support commutativity of the statements. But still lets me kind of separate the two things from each other. It lets me do reasoning, logical reasoning, by looking at one trace at a time only, and then once I have a bunch of assertions that I've computed, come back to check the program, and whatever commutativity properties hold, based on those, it soundly tries to find a reduction. If it succeeds, it succeeds. If it doesn't, it goes back and tries to infer more things. So it's really, really important, because context usually in people's minds are predicates. And context in the automata theoretic framework are actually words. And the fact that they're words is really, really important to kind of let us maintain these two separations from each other and not kind of mix the two things together. Okay, let me move on. So proof checking, the final piece of the puzzle. So now that I know how to represent infinitely many reductions and contextual reductions, specifically using tree automata, I have to just convince you that once I have a set of assertions and therefore a regular language for a proof, I can actually check the proof. I can check this basic proposition that says, does there exist a reduction in the program that is covered or subsumed by this proof? Okay? So the key result is this is decidable using tree automata. So if I have a regular language, which is my proof, and I have a tree automaton that is representing the set of all reductions, infinitely many reductions for the program, I can basically check whether there exists one language element that this tree automaton represents, which is a subset of that regular proof. And more importantly, this is not just decidable. Looping tree automata say that this is decidable in linear time over the components that participate in this, which is really important because those reduction automata are huge. If it was anything other than linear, we would be basically dead in the water in terms of actual scaling up. Now, finally, one last piece of the puzzle related to proof checking. So if the proof is sufficient, I'm done. We can check it, we are done. But what if the proof is not sufficient? What happens to counterexamples? And I want to kind of underline the problem for you and tell you that it actually has a solution. We don't have to worry. So think about the set of all reductions of the program, and I'm only now representing the blue part, the provable part. I'm kind of dropped the rest out. So if you remember, I told you that these slices of the ellipse represent all sorts of program reductions. So I have a lot of these reductions in my set. Some of them are overlapping, some of them are not, and there are infinitely many of them. So when I'm trying to do proof generalization, I take one counterexample. It belongs to some of the reductions, but not all of them, and I generalize the proof and I cover it. Then I take another counterexample, which I haven't told you yet where it comes from, but let's say any counterexample, it could belong to a bunch of other reductions. And I can generalize it, but now I've made progress somewhere else, but not where I had made progress before. And because I have infinitely many reductions, I can basically adversarially, pick reductions every time from a different place. I keep proving things, but I never make concrete, progress where it actually matters for one particular program reduction. And here is the place that I want to kind of make the point at the beginning of the talk that I mentioned to you. In this case, I don't even know what program I'm trying to prove correct. Once I actually prove it, I know which one, but a priori, I don't know what program I'm proving correct. If I don't know what program I'm proving correct, how do I know how to decompose my proof over the structure of that program, which is completely unknown, right? It's very actually useful in this case that I don't commit when I'm doing a proof. I don't commit to a particular program. I just say that here is my proof, here is things that I've proved correct, and here are all the programs. I don't know which one is going to win yet. I will make progress here, and I will basically just check whether one of them is covered. I don't have to try to decompose this over a particular pick or a set of particular picks here. And this also underlines this potential divergence problem, right? How do I pick counterexamples so that I make concrete progress and I can actually show that I would converge? So luckily, looping tree automata satisfy this wonderful property that they tell you that yes, there are infinitely many reductions here. So you could have infinitely many counterexamples if you wanted to make progress across the board. But actually, these are not arbitrary. When you represent a set of languages using looping tree automata, it actually happens to be the case that these are tied and connected together in a particular sense, which then satisfies this property. Whenever you're not covering a set yet, there exist finitely many counterexamples that if you prove all of them correct, you will make progress across the board for all reductions. This completely non-trivial thing means that I can prove those finitely many things and then have a refinement loop that has a guarantee of convergence. I mean, it could still diverge if I guess the wrong invariance. That problem I'm not solving. It's still there. But it will never diverge as a result of a bad choice of counterexample. And that is basically the final piece of puzzle that I need to basically show that, you know, this framework works. So stepping back, I told you a particular way that I can try to do simplifications of proofs of concurrent programs so that if an automated verifier has a chance to actually prove something correct, even if it's not the full program, it could succeed. This also has applications to relational program proofs, things like hyper-safety properties and any sort of relational proof, because there you are automatically, in a sense, constructing a product program where most of the behaviors are redundant, and you're actually actively looking for a particular reduction of the program to prove correct as a means of, instead of all possible relations. So we actually, applied this to hyper-safety verification of concurrent and, sequential programs, and, we had really, really nice results coming out of this. And the absolute final remark, I showed you these kind of two instances, how this particular compositional, but not in a classic sense framework, could be useful and could be kind of exploited to do interesting things. So I'm hoping that I've convinced you a little bit, and the advantages of basically ignoring the program syntax and looking at proof objects as this kind of separate objects that can be kept away from the program only until the last step in which we want to actually do the proof checking test. And with that, thank you very much for listening, and I will be happy to answer any questions.
Time for a couple of quick questions.
There's a question there.
So there.
Okay. Thank you for this very interesting talk. So the one thing that struck me listening to your talk was that logicians tell us that proofs and counter models have a kind of coexistence with each other, and I was just wondering, okay, perhaps what we've done is over-optimized our program syntax to support proofs, and could we perhaps change our change languages so that they support the kinds of compositionality properties you need to find counter models efficiently?
Sorry, I didn't catch the last point. So the library point I didn't catch.
Okay, so no, it's just so something like, say, the while language. It's sort of designed in order to support proof via Hoare logic, like sequential composition and parallel composition with the concurrent separation logic. And so it's like very, so it turns out the algebraic structure of the syntax supports proof very well, but it doesn't do a good job of supporting looking for refutations or counter models very well. So could we change languages to support this kind of, this style of...
Right, that's a very interesting question, but I have really very little expertise in language design, so I don't know how to answer that, but I can think about it and maybe discuss with you further during the break to see.
Thanks for the talk. In stateless model checking, there's been a lot of work on dynamic partial order reduction, and over the last few years, a lot of papers are trying to go beyond what you can do with straightforward dynamic partial order reduction by exploiting things like knowing that these things are going to be writing the same values as each other. I wondered, has anyone looked at using semi-commutativity as a way to go even further with deep
That's
work?
an excellent question, because I was talking really at a very high level. I didn't actually mention that the particular kind of pruning of these trees that I was telling you about, that is exactly partial order reduction. But what
I saw you skipped over a slide that said partial order reduction. I was like, tantalized.
Yes, exactly. So the way that we do it is we pretend that we are kind of traversing the tree as a partial order reduction algorithm, and we prune it exactly as a partial order reduction algorithm would. We would maintain slip sets. We would cut things out when slip sets say cut it out. And the only context that has appeared in partial order reduction is actually quite old. I think it goes back to the 90s. There are this kind of predicate context. They call it conditional dependence. So that there is a history of that, but there is no history of the context actually being a word. It's always states or predicates. And for us, it was really important for this not to be predicates, because we would fall back into the trap of having to bring the proof in. But I did ask, when I was doing this, as a sanity check, people like Parash, Abdullah, those people that have done the DPOR kind of work, whether they have looked at semi-commutativity or contextual commutativity, and they have said no. So the only instance that I know about is this data-centric partial order reduction, I think they call it, that they're looking at read-write dependencies. That one appeared at Popple, I think, a couple of years ago. And this is not comparable to that, because context cannot take care of those sort of things. So that's the only instance of relaxation of the classic results that I've seen so far.
Thank you.
I think we'll have to break here and take the other questions offline. But Laurie wants to make a very important announcement.
There is going to be a fire alarm test at 11 a.m., so 10 minutes into the next break. I'm told it's going to go round the hotel 3 times. So, if you hear a brief thing, you're not going to burn. If it keeps going on, you're going to burn and run. But basically, don't run. We'll have SVs outside the rooms pushing you back in at 11, okay? So, enjoy your break. And thank you.